right now. Thanks for letting me know. But I, no guarantees, guys. I'm not guaranteeing because we're going to be doing a bunch of stuff in person, all that stuff. Again, pretty soon we won't have recordings. So anyhow, so the guy's interviewing accountants. So the guy, first accountant comes in and guy goes, okay, I have one question for you. What's 2 plus 2? And the accountant says, well, of course it's 4. 2 plus 2 is equal to 4. And it says, okay, well, thanks a lot. I'll be getting back to you. Next guy comes in. Again, the interview question is 2 plus 2. What is it? And the second guy says, of course, it's 4. And again, this keeps happening for interviews with these various accountants. And then sort of towards the end of the day, person comes in and they says, what's 2 plus 2? And the guy kind of looks around the office and goes over to the door, locks the door. Then he goes over to the window, draws the blinds, comes back and sits down and he says, what would you like it to be? Okay, so I always thought that meant that accountants are like, the joke was that the accountants are like shady characters or something like that. But in fact, I don't think after years of working with accounting and accountants, I'm not an accountant, I'm not a finance person. I'm just sort of like understand to some extent managerial accounting, which is different. But now I understand what they mean. So accounting is a very, very important topic. And basically, as you guys are concerned, you guys are engineers, business managers, you're not finance people. Okay, so as far as you're concerned, accounting is a tool for you to understand what's going on in your business. The language of business, regardless if you're making semiconductors or rubber tires or social networking, whatever you want to call it, the language of business is money. Okay, and so when you're sort of talking to your business, reading about your business, what's going on with it, you got to be able to look at the language of money. And what the accounting does is it tries to help you understand what money is, what your business doing money-wise. When we're sitting here, okay, talking about money, you may be thinking about money as you understand it in your own life. Doesn't seem like there should be a whole lot of ways to slice and dice money. You have a certain amount of money in your checking account. You're gonna be, you're working at maybe some part-time job or something, or have a student loan. You're expecting a certain dollar amount to come in. You have certain expenses that are, could be constant somewhat. And then, you have like credit cards. So you have like a line of credit or something. And, but it's pretty simple, right? Sort of cash in, cash out. But imagine a business, okay? Imagine a business that, so your typical business, you have a very, very complicated scenario. So let's think about a typical manufacturing business, right? Let's say you're manufacturing part A. Doesn't have to be semiconductor. So manufacturing part A, you're buying. So let's say you're the guys who designed this thing and it's your product. So let's, for the sake of discussion, let's say it gets actually manufactured somewhere else. So you're buying it from manufacturer B in the sense that you're paying that manufacturer, I don't know, like a Chinese, Malaysian, whatever, American manufacturers to make this for you. Let's say they're jeans, I don't know, make it for you, okay? And you're selling it to company C, okay? So how does this work? Well, what happens is, so let's say we got a timeline. So in months, let's say, so it's month 1, month 2, month 3, month 4, and so on. Okay, so here you talk to company C. Okay, so month 1, you talk to company C. Company C gives you an order. So order received for like a I don't know, 1,000 pairs of jeans. Let's say they're expensive jeans from C. Okay, and so what you do is you go put in an order immediately because you're on the ball. You go ahead and same place. You order manufacturing at B. Okay, B might ask you to put in like a deposit or not, but let's say they don't. And then they tell you, look, it's going to take us a while to make you this part. So it's gonna take us 3 months to deliver these parts. So 3 months later, so jeans arrive from manufacturer B. Let's say it takes you, there's like let's say there's just you and some of your buddies working on this thing. So we don't have a lot of hands. It's like a real high-end pair of jeans. You got to make sure you're selling good product to company C. So it's going to take you this long, a month, to inspect the parts. You got to go through 1,000 pairs of jeans. Okay. So when this happens, where are we? So a lot of places, okay, when you get the order in, let's say you had $100,000 in the bank. Okay, let's say these guys asked for 50K up front. Okay, so now you've got it. They gave you, let's say with this manufacturer B, you're a small company, you don't have a lot of negotiating deals, so they give you 30-day payment terms. Okay, so 50,000, that's how much it costs. Let's say you didn't pay anything here, I'm sorry. Okay, so let's say here, okay, they said, let's say you only had 50,000, sorry, whatever. Sorry, I keep changing my stories. I want to show you guys a bad scenario. So here you get the bill from manufacturing B and you have till here to pay it. So here you got to part with your 50K. Okay. Now here's where you delivered the part to your customer. So jeans delivered to company C. Okay. Now let's say this company C is, I don't know, it's Walmart, or no, I guess, I don't know. Walmart, it wouldn't be selling expensive jeans in Walmart. What's a big company that sells expensive jeans? I don't know, because I don't buy expensive jeans.
Use Supreme for now.
Supreme? Okay, Supreme. Thank you. So Supreme, you're still a small company. So Supreme says, you know what, Louis, the only day we'll do business with you guys is we'll pay you on 60-day net. Okay, so you deliver me M5. Okay, now you bill them for, let's say your agreement was to sell them these jeans for $200,000, right? So it cost you $50,000. You sell it to them for $200,000. You deliver it on M5. Okay, but assuming that they're even creditworthy, they're nice, everything, you get paid your $200,000 here, okay? So even with this small scenario, you can see where you could really run into trouble, because let's say you had some employees, right? Let's say you just, your bill, your monthly bill was like, employment cost was like $10,000 a month, which isn't very much, right? Just a few employees will do that. Between, like, if you can survive to this month, you make $150,000, right? But what happens in these from here to here, these 2 months? Okay, you're gonna have to come up with $20,000 that you don't have. Okay, because you paid your supplier, you don't get paid till 60 days later. Okay, so everything, like, it would be great if you got paid, but what happens here? So if an accountant, for example, your typical accountant, typically, depending on what you ask them to look at, if they look at this year, they're gonna say, you did great this year, right? Because you had revenue of $200,000. You had a cost of $50,000. So you made a net profit of 150K, right? From an accounting scenario, everything's okay. But if you didn't have the money to pay your guys to stay in business these 2 months, okay, you would go out of business. So although your accountant would tell you that things went okay this year, you'd be bankrupt, you'd have to close the doors, and that'll be that, right? So this is the difference, and that's a cash flow. So this is like accounting numbers. They talk about profit, loss. They look at accounting periods, etc., right? But you also have to worry about just cash flow, which is like money coming in and money going out. They are both extremely important, okay? If you just worry about cash flow, you can't do things like planning ahead. You can't say, look, my rent is $5,000 a month, so I'm gonna keep track of that. So I'm gonna assume this year I have a $60,000 rent obligation. Every month you're paying $5,000, but you're not looking ahead to plan ahead. If you say, look, my insurance costs are X dollars per month, looking ahead, you don't plan ahead. So like if you buy a car for your business, right? That seems like a giant cost for this year, but the way businesses look at cars or big capital expenditures is they basically apply the cost of that to 3 to 5 years, because you're expecting to actually use that car for several years. So how do you allocate those costs? So those are all done with accounting sort of techniques. But if you don't have the money or the credit to buy that car today, then you can't use it. So that's where cash flow comes important. Okay, so these are all aspects of accounting and cash flow and et cetera. Okay, so that's one thing I wanted to tell you guys. Both are extremely important. Unfortunately, I'm just sort of telling you guys about, like even if you run a small business, this is the part that had not occurred to me before I got into business. Even if you run a small business, like my father-in-law is a truck driver, he owns 2 trucks, okay? And for the life of me, I don't think he'd be able to tell you how much he makes a year, what invoices are outstanding, what money's coming in, what his expenses were, what his profit margin is, because and like it gets really, 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 really complicated very quickly because things are happening dynamically all the time. You're getting money come in, expenses are happening. Let's say your truck breaks down in his case, or you need to, your gasoline card cost just went up, etc. It's hard to match the income to the cost. That's a big part of what accounting does. And the problem is the incomes and the costs are not at the same time in a business, right? You could get, for selling these 1,000 pair of jeans, the income could happen 6 months after the costs incurred, but somehow you have to link those two together. And that's like that's a big sort of the big overall task of your typical accounting activity. But again, cash flow is important, okay? Because if you don't have the cash, you got to close your doors. So that's just a statement about accounting and cash flows. Now let's talk about a typical engineering project, okay? When you're talking about the costs, you can, so costs of, I'm going to say chip design or VLSI design, it's the same thing in this class, but really it could apply to most engineering. Okay, so generally you have two types of costs. You have something called NRE. You will hear about that, no doubt, in your career. That stands for non-recurring engineering expenses. Okay, and then you have something called COGS. What you'll hear, man, you'll be hearing about these a lot. So cost of goods sold. Okay, so what do these mean? So non-recurring engineering costs is, there's a lot of information there. It's non-recurring. It's all the costs that happen upfront as you're designing this part. So let's say you're designing a chip, okay, in this particular case. So what do you have to pay for non-recurring expenses? Okay, so you have to pay for your design engineer's salary. You have to pay for computer aided design tools. Usually license these for some period of time, so you pay for those licenses. You have to pay for what's called mask tooling costs. We'll get into what those mean, but the way you design or the way you make chips is you have silicon wafers, and these wafers go to the factory, and then there is a lithographic process that prints these chips onto these wafers. Okay, so lithography basically means you've got some kind of a mask or some kind of stencil or something like that, and they're using light to basically write different patterns onto these chips. And it's a very, very complicated process, but in the end, it's a lithographic process, and it uses these stencils as and they're called masks in the semiconductor business. And they tend to be very expensive, and they tend to be very dependent on which process technology you're in. But those are examples of non-recurring engineering, because let's say you design this part 3 years ago. You just pay, the cost of the engineering, the salaries for those engineers from 3 years ago. Those guys have moved on to some other products, say, or maybe used a bunch of contractors or consultants. So those happen only once at the beginning of the design project. Same with the tools. You only pay for the mass tooling costs at the beginning of the project, and then you keep using the same stencils over again. So these are all non-recurring expenses, okay? Then, so that's the non-recurring stuff up front. Then there's the cost of goods sold. So every chip you ship, like the millionth chip you send to your customer, has a cost associated with it. So for example, that's the cost of that piece of silicon. Okay, so silicon cost. The cost of testing that part. The cost of putting that part in a package. What else is non-recurring engineering costs? The cost of shipping that part to your customer. The cost of returns, say. These are all, even if you, like your 1,000,001th part will have these costs as well. Your 10th million part will also have these costs. So these don't happen just once, they happen continuously on during a project. There's also the cost of, let's say you have what's called sustaining engineering costs. Usually when you're in manufacturing, somebody's making sure, like a different type of engineers, manufacturing, those kind of engineers are always keeping an eye on things, making sure everything's okay. So like the sustaining engineering, you have to put those costs in the cost as you ship. Okay, so almost every, and I can't imagine what type of engineering product doesn't have this. And maybe an example is like software. Like different engineering projects, these will be very different from each other. Like if you think about software, this cost of goods sold is almost like zero. Probably the only cost that you have of your software distribution is maybe you pay for, I don't know, the Amazon Web Services or something to download the software, or maybe you're kicking some percentage back to Apple or Google if you're using I don't know how that business model works, but maybe you're using them to distribute your software. You're paying some like support engineers to support the software users, but your cost of goods sold for software is very low. But upfront, your NRE might be quite high because you'll need a lot of software engineers to write the program, okay? And some other businesses, their engineering activities are pretty small. Maybe they're just modifying an existing product. Maybe it's not even a chip at all, so there's not a huge mass tooling cost. Maybe it doesn't have a lot of computer-aided design costs. They're modifying, I don't know, they're modifying the case of a computer and selling it as like a ruggedized product. So that's actually a good example. Let's say you have a consumer computer or a consumer iPad or something like that, or a tablet, consumer tablet, and now you're going to sell it as a ruggedized version. So all you're going to do is you're going to redo the case, no re-engineering of the insides, but then because it's ruggedized, that case is going to cost more than the consumer version. So your NRE is low, but your cost of goods sold is high because you need a rugged case that can get run over by a car and still survive, and so on. Okay, so you can kind of divide it up into those. Okay, so this is left over from, so now let's use I was going to use an example. Okay, so let's say for the sake of discussion, this is how you use it in a chip design. Okay, let's say you guys are, created a startup, you went and raised, $5 million for the sake of discussion. And your idea is to design a chip that does network processing. I don't know. So I'm just cooking up some random chip. Okay, so, okay, great. 5 million bucks in the bank, life's good. Now you got to figure out, or you're trying to figure out, is this enough for you guys to, if you're smart, that's what you do, is you plan it ahead and then go ask for enough money to be enough. But let's say it's 5 million bucks is what you have, okay? So your product does something. So I'm gonna draw a chip, okay? Let's say it's got some proprietary logic that does, maybe it's like artificial intelligent algorithm, I don't know, that does something that the world will be excited about. It's got, you'd love it for it to have a lot of memory. So this is called SRAM. It stands for static random access memory. You need a lot of high-speed memory in there. And then you would also like to, you've talked to customers and they've told you that it's very important to have a USB 3.0 interface to this chip. Everybody with me so far? Any questions? Everybody's familiar with like USB 3.0, different USB standards, memory on chip. I just picked memory because it just typically takes a lot of space. So, okay, so let's look at what this would cost you. Okay, so the proprietary logic, it's what's your sort of your magic recipe. Let's say you and your buddies came up with this proprietary logic. That's the whole point of this thing. So that for sort of NRE costs, that means that you need a certain number of design engineers to basically take that algorithm that you have and maybe you create a Verilog with it. One way or another, it goes into some, either you go straight into custom schematics depending on what you're doing, or more typically Verilog, you do synthesis, place and route, and then it finally goes into what's called a physical implementation. So this is something that can go on the stencils, go on the masks, so physical implementation. So you need these design engineers, okay? Then the other thing you need to do is you need this USB 3.0. This is called, don't ask me why, these are called cores in chip conversation. So you might have, a core is like usually it's referred to some typical functional block on a chip. So like you hear about a USB 3.0 core, or a PCIe core, or a memory core. You never hear about a proprietary logic core. It doesn't work that way. So these are like sort of typical cores, or like a memory. The memory interfaces are DDR, DDR2, DDR3, DDR4, DDR5. So those are like memory interface cores. Okay, maybe in Xilinx, I don't know how many of you guys have experience working with FPGAs and stuff, but it might be the same language there. By the way, I'm not sure, I don't know how to do voting or whatever. Maybe, how do we do that? I don't know, can we do voting? No, I was just wondering how many of you guys have actually worked on FPGAs. But anyway, hopefully some of you guys, so it may make some sense, somewhat similar. Okay, so, but going back to our USB 3.0, what happens with parts in chips that have, so something like a USB 3.0, you can't design that willy-nilly. Like here, this is something that your friends created. It does some function that you're saying it should do. Maybe it does a little bit more, maybe it does a little bit less. It's okay, maybe it's okay, right? When you're selling a USB 3.0 capability on your chip, it has to exactly adhere to the USB 3.0 standards, okay? Because your customer that's buying this chip, they're gonna, connect it up to a microprocessor that's claiming it's, does USB 3.0. If they can't talk to each other because you screwed up this USB 3.0 interface, then you're basically screwed. Okay. So, and these interfaces like USB 3.0, PCI, DDR, Bluetooth, these different standards have okay. Kyle was saying generally thinks of a core as something interchangeable with another similar solution. That's good. I like that. Well, anyway, they use it. That's the verbiage for core. So anyway, this USB 3.0 might have like a 200-page description or more. Okay, and there's like standards committees come up with every nook and cranny of this thing. Long story short, a lot of times with these USB standards, the food chain, value chain, silicon chip design environment is you go buy this core from somebody else. So there are companies that specialize in building a USB 3.0. They'll have a USB 3.0 core available. It's like a library part. They've already run it in silicon. They've already checked it versus the standards. They paid a lot. And their business is they're selling it as what's called IP. So by IP stands for intellectual property. So in most of the rest of engineering, IP or intellectual property stands for patents, copyrights, those kind of things. I've only seen this in chip design. Intellectual property IP blocks stand for these cores that you buy. So if you want a USB 3.0 core, you actually go to the company and you say, hey, do you have any USB 3.0 IP? I don't know why, but that's just the only place that they call it IP. So if you're doing chip design, you're going to go look for these IP blocks, so-called. Okay. So I want to buy that IP. Okay. USB 3.0 is relatively new. Okay. So it's probably going to be a more expensive thing that you buy than the USB 2.0 block, right? The USB 2.0, that company made that, I don't know, USB 2.0, when that come up, I don't know, 20 years ago they did it. They've sold a bunch of it. The price is down. Now, just like anything else, you sell it enough, it's old enough, prices go down. But USB 3.0, I don't know how long it's been around for, 5 years, 6 years. It's still relatively expensive. Okay, so but you probably need to go outside and buy it from a third party. Okay, and then you also have to pay for the mask set, or this is the stencil. Okay, so how would you come up with numbers here? Well, let's say you kind of know you've been around the block, done this enough, and you know that you're expecting that you'll need 4 design engineers to work on this for 12 months on this design of not just the block, but putting it all together. And on the average, they make $250K per year. I mean, maybe they make $250K a year, or maybe that's their salary plus all the other costs, right? When you have an employee, you got to pay their salary, you got to pay for their Social Security taxes, you got to pay for their health insurance, dental insurance, you got to contribute to their 401k. When you're paying somebody $150,000 a year, they might cost you somewhere, I don't know, maybe $250,000 a year. It depends on what state you're in, what the costs are, et cetera. So anyway, but let's say you did that. So that's about $1 million of salary. Okay. So, and then you also, to do all this, your stuff, you have to license some CAD tools for that year. So let's say your CAT tool license ended up costing you 500K. Let's say this USB IP, because it's expensive and new, it's also gonna be 500K. Okay, so let's say you decided you're gonna make this in, pretty good process. You're not gonna go to the bleeding edge. The bleeding edge process now is like 3 nanometer. Let's say you wanted to make this in a 28 nanometer process. Okay, if you remember, 28 nanometer means 28 times 10 to the minus 9 meters, which is I don't know how to compare it to anything we'd be familiar with. I think I want to say it's like 10th the size of a virus, but I'm not sure. Maybe it's on the order of size of a virus, maybe like 5 times, 10 times smaller than a virus. A very small thing. Okay, and that refers to, we'll get more exact about what this refers to as the class goes on, but it refers to roughly how big a transistor can be in that process. Okay, so 28 nanometers is still fairly expensive, but it's not the most expensive thing. So the mask set then will cost $5 million. Okay, so if you stack all this stuff up, this is gonna cost, this whole thing, the NRE is gonna cost you $7 million. Okay. Any questions about any of that stuff? And a typical chip has like a bunch of these IP cores. And it's kind of hard. It has a bunch of different things, designers and things. It's hard to estimate this without a lot of practice. Mask set cost is very dependent on what's going on, and the CAD tools depends on what you're exactly designing.
So the smallest chipset that we have is 3 nanometers, Professor?
That's what's coming online. So my brother works for Qualcomm, which is, they're a big company down in San Diego, makes chips for cell phones. And to him, 3 nanometers is still, they're trying to qualify it still. So it's not a production. It's available, but I don't know if they have products running through it. But yeah, 3 nanometers is where it's at right now.
And this would be for like, what would be an example of an application? Like maybe like a chip for a camera, right? Or something like that. Would that be like a good speculation on the, on like the chip that you could use, the chipset that you could use for that?
For 3 nanometer?
Yeah.
Yeah. So, okay. Well, let me tell you about that. So this is a very important question you're asking. So like this, were numbers I came up with for a 28 nanometer process. Okay. As George mentioned, we're in 3 nanometers, we're the bleeding edge now. By the way, also, it's not a continuum of it. It's not like things go 28 nanometers this year, 27 nanometers next year, 26 nanometers the year after. That's not how it works. So what happens is you have these steps, okay? So these are the process technologies. So the bleeding edge is 3 nanometers. Okay, so for a place like a NVIDIA or Qualcomm, someplace like that, their sort of stuff that they're doing production right now is either 5 nanometer typically or 7 nanometer. So this is being qualified. Means this being qualified means that everything's there, the factory's there, the process is there, they're running parts through it, but they haven't made sure they can get enough parts through it in the sense that you haven't rung up all the manufacturing issues out of it. So that's where kind of the 3 nanometer is at right now, is my understanding. Okay, so their bread and butter stuff for NVIDIA, Qualcomm is 5 nanometer, 7 nanometer. So then, like, you know, if you think about Apple's, I'm just making some of this stuff up, but it's kind of roughly about right. So if you're talking about someplace like Apple and their M1 chip, maybe here in like 10 nanometer, say Apple M1 maybe, I don't know. And this is where sort of like Intel, so Altera FPGAs are here at 10 nanometers and 12 nanometers. And then past this, you know, you also, there's 14 nanometers, different places have slightly sort of in the low teens. And then past this, you go into 22, 28 nanometer kind of thing. Okay, so this is, trying to think of who this would be typical of, but this is like where things are, like when you said image sensor, most sort of the Sony image sensor or something like that might be here. And then you have 45 to 65 nanometer. And so a lot of ASICs, a lot of digital ASICs, application specific inner circuits are here. Okay, so why is that? Okay, so it turns out, you know, obviously, if you guys remember, I mentioned that these refer to roughly a dimension of length of the transistor on a chip. So something that's 3 nanometers, you might be able to put in, I don't know, 10 to 20 transistors compared to a 10 nanometer part. And things just run faster and all that stuff. So it's much better. Now the problem with, say, let's just take 5 nanometer, okay, for a second. The problem with the 5 nanometer chip is, you know, we talked about a total NRE of 7 million for a 28 nanometer chip that's out here. So this was 7 million in our example. If you pick an example here, okay, so what you'll see is a number that is maybe 20 times that 7 million. So the mass cost here, I really don't even know what it is. I've never done a project in that mass cost, but mass cost maybe, let's call it 20 to 50 million for just a mass set. Depends on what company you are. You know, Qualcomm probably gets a better deal than somebody else, whatever. So those are the mass costs. We talked about IP cores because, you know, remember I mentioned that you go license these cores from companies. Well, those companies would have had to make these IP cores, tested them in silicon way before Qualcomm. They haven't had a lot of customers here. So the IP cores may be very, very expensive. And they normally don't have like a USB 3.0. They might have 20 different IP cores for that, you know, is in there that they need to get. So let's say that all in totality, and each one of those IP cores might be like 3 million, 5 million, 8 million. Some of them are 1 million. So let's say in total, those IP cores are going to cost them 50 million. Okay. So those kind of complicated chips, they won't have 4 designers, you know, at a place like Qualcomm. They have a whole ton of designers. They have a whole ton of test engineers, qual engineers, people who are working with the fab to make sure things are okay. They have program managers, they have application managers, they have software people that are writing firmware for this chip. So they might like have, I don't know, like 100 people total working on this chip for a year. What does that end up being? So 100 people, So that's 25 million bucks. Mass cost, IP core. Okay, they might have like, they're paying CAD tools, using high-end CAD tools. Let's say that is another, I'm just throwing out numbers, but these numbers are probably not, I mean, there might be a factor of 2 off, but I'm not like exaggerating, or this is my best guesses. Okay, so the CAD tools might be another, 10 million, because you got to get all these guys 10 million CAD tools. So on the high end, I mean, it may not even be the high end. You're looking at something that costs $100 to $200 million of NRE to design, let's say. Now, this is another thing, right? Like the other thing is, when we're talking about mass costs or these people costs, we're assuming one iteration of the design is going to get it there. That's sort of almost never the case. You get the part back, you get engineering samples, you kind of test it out, and you go, shoot, didn't quite work. You have to iterate it. So, take whatever is your first guess, and you might have to multiply by 2 or something. But so let's look at this, $100 to $200 million. It might be even more, right, George? So a big dollar amount. So that's the NRE that they paid up front. Okay. And I'm not going to even go into how many wafers they need to run, whatever. So think about how many markets in the world can sustain that kind of cost, right? So if you're going to pay an NRE of 100 to 200 million on that part, okay, plus you're taking a risk, then there's the cost of goods sold, right? So it's not like every dollar you make goes to you. There's the cost of the material, got to run a bunch through, and so on and so forth. So if you're spending 100, 200 million, you're probably looking at getting 500 million to $1 billion in revenue back, or hundreds of $1,000,000 in revenue back, okay? And you're basically, that's can't be just guesswork in a place like Qualcomm. You better be pretty sure. Let's say you're looking at $500 million per year of revenue back. Because also the lifetime of a lot of these chips isn't that long. It might just, the whole chip might take 2 or 3 years. That's all that you're going to run it in production before it becomes obsolete in some of these high-end things. So think about it. How many markets are there that can give, and how many chips can feed those markets that are giving you $500 million in revenue back a year? Not many, not many. Like if you're in mobile phone applications, okay? A lot of cell phones get sold. So if you get designed into a cell phone or several cell phones, you're going to make a lot of money. Okay, so mobile cell phones. Some automotive products are starting to get to bigger numbers. They're still much less than cell phones in terms of volume, but it looks like it's starting to get attractive. Okay. Then you're looking at maybe laptops, maybe, or like tablets. It's again not as high as mobile phones, but some high volume parts. And then maybe things like GPUs or something like that for, server farms or those kind of things. But the volume is going down on those, but the revenue per chip going down. But like, let's say you were making a medical product for a particular medical applications. How many medical products, I'm just talking about the chip now, part of it, are going to give you $500 million in sales a year? I can't think of any. So basically, once you get past that handful of parts, like so basically parts for mobile phones, parts for laptops or servers, automotive, and again, like mobile phones by far is like bigger than those guys. When you get away from that handful, I can't think of too many things that are going to give you your money back on $100 to $200 million investment. So like even if you make a camera chip right now, like those are kind of like maybe sitting out here, the logic part of them. Maybe they're getting down to 12 nanometers. I saw Samsung just announced a 12 nanometer, but it's pretty new. Most of the stuff going on is out here. So what you do is and I'm glad you asked that question because it gets to the core of NRE, okay? You've got to come up with the cheapest process that will do what you need it to do and design your part in there. That's how chip design, the engineering, meets cost, okay? Meets NRE cost. That's the overlap, okay? So because you could say, hey, look, I can make my chip. It's not going to take me much engineering effort to, this process is fast. It's a 28 nanometer process. I don't have to put a lot of effort into my Verilog code or whatever. I just write a Verilog, synthesize, place and route, plug it in there, and runs no problem at the clock rate I needed in a 28 nanometer node. Okay, great. But guess what? It's going to cost you $2 million. It's going to cost you $2 million more to use that node than you have. You don't have that money. Okay. So now you need to look at another node, maybe like a 45 nanometer node, where the mask set may be 2 million, not 5 million. So now it's in your budget, right? Now you're talking about 4 million. So you say, okay, can't do it in the 20. So this is, again, I'm talking about, this is where it feeds into engineering decisions. You go, crap, I really wanted to use that 28 nanometer process, but I can't. Can I use, is this still a viable product in a 45 nanometer process where my NRE is going to be more like, so this is at 28 nanometer process, might be 4 million total NRE because this will go to 2 million. I don't know if I'm doing this right in 45 nano. So now what you might end up doing is now this design maybe just got a whole lot harder. It's the same algorithm, but it's running in a slower process. You may only be able to do the synthesis, place and route, or sort of lazy design with Verilog. For only some slow parts of this, you might have to pull out the high-speed data paths and say, you know what, I have to like hand tune those high-speed data paths to go at 40, go to right speed at the 45 nanometer process. So going into an older process puts a lot more constraint on the performance aspect of the chip. And for any market, the market's looking for a minimum level of performance. You can't just say, well, I'll just give you the performance that a 45 nanometer node allows because that's my budget. If you don't get the performance you need, doesn't matter how much money you spend on NRE, you can't sell it. You don't have a real product. Okay, so this is where you come in. This is a link between NRE costs and performance. That's the trade-off there. So that's why, when you're looking at your presentations, you say, okay, I'm going to take this part that was made 20 years ago in a 90 nanometer or 130 nanometer process. I'm going to get a lot of performance with it in a 28 nanometer process. Well, that might be just too expensive. You may not be able to make the case for it for that to make sense. Okay, maybe you can make a case for doing it in a 45 nanometer process or 65 or something like that. But anyway, that's a trade-off when it comes to NRE. Okay, so that's the first component, NRE. Any questions about that, guys? So another thing I wanted to mention about NREs, you may realize, crap, like I can't afford, maybe you're still over budget. I can't afford to have USB 3.0 in there. Maybe my customers will accept USB 2.0. Okay, let me go talk to them, see if I can talk them into using USB 2.0 because that'll only cost me 50K instead of 500K because it's an older IP core, and I can use that. So that becomes trying to really test the market, talk with your customers to see if you can go to this older um, process, older IP blocks as well. Older stuff generally costs less, but it has lower performance, okay, from an NRE standpoint. Okay, so that was NRE. Now let's talk about cost of goods sold. So this is every part that you ship, okay? So basically what happens is these, let's just think about the silicon price, okay? So these silicon pieces get made on wafers. So they get printed on these wafers. So these are like the chips that get printed on. And these wafers come in mainly in two sizes, either 8-inch or 12-inch. Most of modern wafer sizes are 12-inch processes, okay? So basically that refers to the diameter approximately of the wafer, silicon wafer, 12-inch. And sort of more exactly, it's 300 millimeters. But, you know, of course, the US has to be English units, so it's 12-inch. And the 8-inch wafers are 150 millimeter. So that's more for like older processes. Okay. So now this is what you got. So if you go to a 28 nanometer process, again, everything's more expensive in a 28 nanometer process. They might charge you, say, at a certain wafer volume, they might charge you $4,000 per wafer. This is very dependent on who you are, how many wafers you're running, and so on and so forth. As you run more wafers, they might give you price breaks and so on. And then the 45 nanometer process might be only $3,000 per wafer. You say, okay, so even from a cost of goods sold standpoint, my 45 nanometer process is less. But it's not so simple because your chip might physically end up bigger in the 45 nanometer process than a 28 nanometer process. Remember that the main difference between these processes are the size of transistors in the process. So if you're saying, I'm going to cram this amount of logic, this amount of memory, this amount of IP in this chip, it might end up being, you know, I'm just going to make up some numbers, might end up being a 15 millimeter on a side chip. Compared to a, I don't know, 20 millimeter per side chip in a 45 nanometer process. And so, okay, well, you know, you pay per wafer. The foundry doesn't, the manufacturing plant doesn't care how many you can fit in. They just charge you per wafer. So if they can cram more stuff in there per part, it's going to cost you less, just geometrically, right? If you can fit more of these guys into your wafer, into your that area wafer, it's going to cost you less per part here than here, of course, depending on the wafer price. Okay, so let me share with you guys, but there's more to the story, because let me show you something here. There's more than geometry involved here. Okay, so sorry, I wasn't paying attention to some of the chats. It says, what about electric cars? Electric cars are super cool, but when you look at them at the moment, they're like a tiny part of the automotive market from what I know, but hopefully there'll be a big deal. But like, just imagine how many cars Tesla sells compared to how many cell phones Apple sells every month. It's orders of magnitude. Of course, there's more chips, more ICs in the Tesla than in a single iPhone, but it's still much, much smaller. And then Kyle asked, do you think the practice of binning chips, especially in the high performance GPU and CPU industry, should be regulated? I don't know what your beef there is with I guess maybe you're unhappy about the way they do binning chips, but generally I'm one of those fascists who thinks business should not be regulated, period. So I'm against regulation, period. But maybe it should be. I don't know. Okay, so let's see. So guys, can you see this web page? There's like a circle there with a bunch of green and things. Okay, so
Yes.
when you're there's a bunch of places that, like websites and Excel sheets, that you don't want to do this geometric calculation by hand, but I'll show you this actual stuff we use at work to try to estimate how many parts we get per wafer and so on. So basically the way they work is you give it a die size. In our example, we said 20 millimeters by 20 millimeters. Well, let me pick the first one, 15 millimeters by 15 millimeters. And so that's the size of your chip that you print, okay? There is, because the way we'll see this when we're talking about processing of the wafers and so on, is so first they make these wafers, then they actually take a physical saw, okay, like a circular saw, and they slice through the wafers. They slice, I don't know if you guys can see my cursor, but first they slice vertically, then they slice horizontally between the chips. So then you can pick up the individual chip, put it in a package, wire bond it or connect it to the package pins and sell it to people. But it's actually like a physical, like a saw dicing. It's like a very precise diamond saw, expensive saw, but it does that. So you have, long story short, you need to put some space between you can't just butt up the chips next to each other when you print them on the wafer. You need some spacing so you can saw through. And that's called the scribe lane. So horizontal scribe lane, you need to include that in your calculations, unfortunately. Then in this case, it's a 300 millimeter wafer. So I said 300 millimeter. You're saying there is like, you can't put the parts right up to the edge of the wafer, because the manufacturing plant needs to grab this wafer somehow from the edges. So you assume that parts that are, too close, this says if it's more than 5 millimeters close to the edge of the wafer, if any part of that die is 5 millimeters to the edge of the wafer, it's not usable. So for example, this yellow one here, this yellow one here, this yellow one here, these are no good because their corners are going into this edge, okay? So up to this point, okay, with all these numbers, don't at the moment try to ignore these things bottom here. Basically what you end up is a map. This is called a wafer map, okay? This tells you the total maximum number of dies per wafer is in bottom here is 256, okay? So in our example, if I manage to get a 15 millimeter by 15 millimeter chip done with a 28 nanometer process, I can get 256, I'm gonna write those down, 256 of those parts in a 12-inch wafer. Okay, so I'm gonna compare that if I have, and that's, remember, that's a $4,000 wafer. And now because of, if I want to compare it to a 45 nanometer process, it's going to give me a bigger chip. Let's say the scribe lanes are the same. So I just changed it 20 millimeters, 300 millimeters here. And I only get 137 die per wafer. This is called, by the way, it's called gross die per wafer. You'll see in a minute why it's called gross die per wafer. By gross means total, I guess, not that it's disgusting. So gross die per wafer is, again, it's like typical conversation. So
Professor,
yeah.
does a circular wafer yield more product than a square wafer, even with the waste?
Yeah, so there is no such thing as all wafers are circular. There's no square, or square wafers don't exist. So you're only stuck with circular wafers. Yeah, so anyway, yeah, it'd be much nicer to have square wafers, but all the wafers are circular. I'll give you a little digression about why they're circular. Okay, so these silicon wafers are, that I can say it with huge confidence, are the purest thing that mankind makes. Okay, so you want to talk about the purity of the material. Let's say you're making steel or copper, or I don't know what else people make, but the purity of silicon as the base material for these wafers has to be very pure. Okay, there's always contaminants and stuff in anything you make. It's hard to get 100% of anything, but these are as close as mankind gets to anything. And so the way they make it is, this process has been around for a long time, is you end up, this is like a very simplified view. I've never seen it be made, but basically they told us in grad school. So what you end up with is you have like a container of molten silicon. Okay, so you start with a very tiny seed perfect silicon crystal. Okay, because also, another thing I want to say about perfect, it's not just the number of contaminants in the silicon wafer, but it has to be in a perfect atomic matrix. So for example, you hear about sand on the beach is silicon, right? Oh, there's all this sand that's silicon, whatever. Yeah, it's silicon. The material is silicon, but they're not perfect crystal lattices all lined up perfectly. That's what we need to make these wafers. So what they do is they start with a seed part, okay? And then they very, very, very slowly, I don't know how slowly, it might be a matter of days, a matter of weeks, a matter of months, they sort of pull this from, they touch this molten, whatever, silicon, pure silicon, and they gradually pull it up, okay? And as this thing cools, as the seed cools, it cools in a perfectly crystalline lattice, and it comes up, okay, they slowly pull this up. Imagine as it's cooling, it starts looking like a big, like, I don't know, think of it as like a salami or bologna thing. It comes out as the cylinder out of this vat very slowly. And this is just like a cylinder of silicon with a diameter of 12 inches, okay? And then once they've made this, I don't know how long it gets, whether it gets a meter and 12 inches or whatever, they dice it crosswise and end up with these wafers that then they sell to the fabrication plants as pure silicon. So because that's our only manufacturing method for making silicon wafers, the silicon wafers all end up being circular. And it's a pain because, yeah, it's like you're trying to, and all die are square or not square, rectangular. So you're always putting something rectangular on a circle and you end up with a bunch of wastage. Does that answer your question?
Yeah. So
Yeah.
when you hear about the silicon lottery, it depends on that process of how perfect that structure is.
That when you hear about what, sorry?
The silicon lottery, like how well your chip performs.
I'm not familiar with that term. Can you tell me more about silicon lottery?
Basically, like when you get a chip and you want to test its performance through overclocking or what have you.
Oh, not quite. We'll get to that later in the class. There's like stuff that comes ahead of it, but I'll talk about where this purity comes from, like right now. But what you're talking about is more stuff we'll talk about in a little bit on the wafer.
Okay.
Professor.
Yeah.
I have actually 2 questions regarding the manufacturing of it. So that means that the average price of a chip would be like around $10 to $15 ish. Like, is there like such a thing as a high price for a chip and a low price for a chip? Like an average price that you would know about?
Oh, are you talking about price or cost? You mean cost
Price
to the
per chip.
customer?
Price per chip.
So is this the price for the customer or the cost in the manufacturer?
Manufacturing section, yeah.
So, it depends on the size of what you make. For example, like a microcontroller, right? Like I don't know, 8-bit microcontroller or something like that. The price to the customer might be 20 cents, 30 cents, I don't know, so to the customer. So the manufacturer, this thing would cost like a dime, 10 cents, 15 cents, something like that. Like a camera chip, depending on what camera size is, let's say it's like a 2 megapixel or something, you go buy it in China, might be like in high volume, it might be $1 or $2. Okay, so those are definitely very inexpensive chips. A large FPGA chip from Xilinx, that's probably going to be a couple of $100. So it really is a pretty big range. Is that
just
kind of
depends
where
on
you
how
were
much
going
application.
to?
Yeah.
It depends on how much application, but also it depends on physically how big the chip is, what process the chip was made in. Like imagine if you had it, like, this is a good example. Like, I don't know if you guys are, unfortunately, you guys can't, you don't really see it in digital much, but in analog, you see it still. Like there's some of these parts that, I don't know if you guys have played with like just analog parts on a printed circuit board, but it might be like a quad op amp you buy from Analog Devices, like a 741 op amp. They're still making that. They like designed it and fabbed it in some like 10 micron process back in the 1970s. They're still selling it, basically like cost nothing to make that part. And so it's very cheap. So, but like if you have a very small chip physically, and it's in an older process, it costs less. Okay, the bigger it is, the higher the performance, meaning it's in a higher end process, costs more.
Oh, okay. And then my second question, actually, I don't want to take too much time. So I see that in the wafer, you see that there's a lot of defective dies, wasted dies, good dies, partial dies, right?
Yeah.
Say that the proportion is not correct. Say that like there's a lot of defective dies on this silicon wafer. Do they still charge you for the wafer?
They will. They'll charge you the same darn thing.
Okay. No.
Now, it all depends. Okay. Now, what they're telling you when you go to the manufacturing place, okay, this is really like a lot of things in business, there's no tried and true. There's no definitive. It all comes to business negotiations. Okay. You could, if you're like, I don't know, NVIDIA or Apple, and you're going to a smaller manufacturer and you say, look, your yield, by yield is how many good parts you have, really sucks. I'm not getting the number of parts I want. I want a discount per wafer because you're just not manufacturing like I want to. Yeah, you're probably going to be able to get a discount out of them. Okay, because their yield isn't that great. And they'll come back and renegotiate the price of the wafer. They'll say, look, this business doesn't make any sense anymore for me because of your defects. the cost per part, I just have fewer costs per wafer, you need to reduce the pricing for me. That kind of stuff happens all the time. Okay, but it's more like business negotiations than the manufacturer telling you, if I have X defects, you'll charge this much. If I have this much, to charge this much, if this much, this much. But then this negotiation of adjusting the prices happens all the time. Okay, and I'm assuming it happens in all aspects of business. I'm only witness to it in the semiconductor business, and the reverse can also happen. Like, you guys have heard about pandemic. Well, I don't know what was the pandemic, but anyway, there's a semiconductor shortage. So basically, these fabs came to my friends' companies. I won't mention the company names. And then they're like, well, we're going to have to increase your prices by 10% or 20% of your wafer costs. Why? Well, because we're full. So the price changes happens all the time, but it's more a matter of you being able to go there and negotiate. And you can imagine you have a lot more negotiating leeway if you're an Apple than when you're a 10-person startup that isn't buying too many wafers. Okay, so the more wafers you buy from a manufacturer, you're like a VIP there. They're counting on your business. You're going to get a lot more consideration than if you're only buying a few wafers. Does that make sense?
Makes sense.
Okay. So by the way, as another segue, I used to have a very big automotive parts customer so let me take one more step back. Whenever you're selecting a fab partner, okay, you really have to think about two things. One of them is the performance of the part of the process. Is it the process you need? Is it 45? Is it 28? Blah, 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 blah. The other one is the business model with, is there a good business fit with this manufacturer? And so there's a lot goes into that business fit. Obviously there's the price that they give you. There is the reputation as a quality, just like any other type of thing. Some manufacturers are known for their high quality. Some manufacturers are known for being cheaper. And so you got to, I wouldn't say always go with the highest quality or always go cheaper. It depends on what market you're in. But in addition to those, for example, this in like say automotive market, which is very, very different. I think medical may be also kind of like that, maybe some other ones. But for automotive, like this parts supplier, which is a pretty big company that were like, maybe like say, call them a $10 billion company. They didn't want to deal with like manufacturers that were too much bigger or too much smaller than them, because they didn't want something that was too much smaller. They would worry about them not being around because, their lifetime of their products, or 5 years, 10 years, 15 years that these parts have to run in cars. So they wanted to make sure those manufacturers had some, could last. But they didn't want to be, they wanted to be important to the manufacturer. They didn't want to get lost, going to a very large manufacturer where even as a $10 billion company, they're not like an important customer. So you got to think about all those things, and companies do think about all those things when they select vendors. And I, it's when you're a small company, when you're a startup, you don't have any choice. You kind of go where you can. But as you get sort of bigger, you start trying to think about all those aspects, because you want to be able to go there and try to tell them, look, my business has changed now. It's fine what we had in our business agreement, but we really need to renegotiate. We need to change something. We need to get me more wafers per month, or we need to reduce the price, or I need to reduce the price for the next 6 months because I'm having business difficulties for the next 6 months and things are going to be better next year. That's, you want to have that relationship, okay, to go talk to these guys. So that's more, you know, you see that in all sorts of businesses. Okay, so sure. So back to our example, okay, guys. So in this, we went from a 28 nanometer smaller chip to a 20 millimeter 45 nanometer. So let's run that. I'm just going to put those dollars into my little handy dandy calculator. If you guys remember, I said 28 nanometer process is $4,000 per wafer. We get 256 gross die per wafer. So I'm just going to run that. That's not what this thing is going to cost you, but let's say I just run that in my calculator, and that's $15.60 per chip there. And in the 28 nanometer process, and the $3,000 per wafer at the 45 nanometer process, I only get 137 parts there. It's actually a higher price. It's actually $21.90. Okay, so okay, that's interesting. So ended up being the 45 nanometer process actually gives you a more expensive part if you just look at geometrically how many parts you get per wafer. And in fact, significantly higher, right? It's $21 to $15. But there's a couple of other factors which even affect the cost just as much. Okay, so that was the geometrically how many parts you could fit into a wafer. But going back to the quality of the silicon wafers and other manufacturing defects, every manufacturer has a so-called defect density. You see it here in this box. And this is, by the way, this is not something they give you very easily. It's like a very closely guarded secret. I don't know if you guys can see my cursor, but it's number of defects per square centimeter, and they're random. Okay, this is what, assuming nothing goes wrong in that particular manufacturing batch, nothing weird happens, you're just going to get a certain number of defects on the average per square centimeter. You're not guaranteed to get that number on the average, okay? So what this tells you, okay, is that it's bigger die, bigger chips are even more expensive than just their physical size, rather than just fitting them, more of them into a wafer. Because if you have the same number of defects per centimeter squared, if you have a bigger chip, you have a chance that more percentage of your parts will get knocked out by that defect than would like a small number of chips. Let me just show you guys that. And this is like a very, 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 very important thing. So let me do a drawing for you. There's kind of a drawing on it. Let me share my screen here.
Professor.
Yeah.
Is that why the wafer price is more expensive on a smaller chip?
No, the wafer price difference is just, can you guys see my screen?
No.
No,
we cannot.
Let me pull it up. No, where is it? Where is it?
We can see your browser, but we cannot see the whatever else you're working on.
Let me see. Start, yes. Okay. So this price per wafer is only coming because this guy is a tighter process. It's a 28 nanometer process. versus a 45 nanometer process. So let's just assume it's in the same manufacturing line, but one of them is 28 nanometer, the other one's 45 nanometer. Does that answer your question?
Is it like the quality of the mask, pretty much, like the quality of the printing? It's still the same wafer, right? It's still a silicon wafer, regardless of which one you do.
It's the quality of the mask, but it's more than that. I think it's, when you think about it, a lot of it is amortization. Okay, so this 45 nanometer process, that cost the manufacturer, like, let's call it $2 billion 10 years ago to build. Okay, since then, it's been around for 10 years. They've recovered their 2 billion, and now they're just printing money, let's say, more or less, in this process. So it's more competitive, right? Now they can reduce the price to compete with other vendors to get more customers, because that they've paid for their initial costs. This 28 nanometer process, let's say they paid $5 billion for that factory 5 years ago. So they still haven't paid it off. They still have to, part of that wafer price has to go towards making their money back. There's fewer competitors that offer this 28 nanometer. So they naturally can keep their prices a little bit harder. There's less pressure pricing here. So those are the main reasons. Does that make sense? I mean, this is just business, right?
Okay, so it's more of a business aspect then.
More of a, mostly a business aspect on the price per wafer.
Gotcha.
Yeah. And so that's, and then, so let's say if you go to a different manufacturer, it's possible they don't have a brand name. Maybe they're not known as a high quality provider. So for them to compete, maybe their 28 nanometer process might be, $3,500 per wafer, and their 45 nanometer process, $2,500 per wafer. So there's a difference depending on the quality or perception of the quality, but it's kind of the same difference that you see in all branded products. If you go clothing or, watches or cars or whatever, places that have a good brand, their branding says quality, they charge a premium. Places that have a brand, the branding says cheaper, they charge less. So those are all come into the business, okay, in terms of the wafer pricing. But primarily right now, we're just assuming it's a difference in process. And one led to a bigger chip and one led to a smaller chip. Okay, so now let's talk about how it's not just geometrically effective. So I'm going to draw a circle as best as I can, and I'm going to put some defects on it. So here's a defect, here's a defect. I'm just going to randomly draw defects. Okay, so I'm going to copy, so to do a apples and apple comparison, I'm going to copy this. So this is like a very theoretical exercise, because if you get the next wafer going through this production, you would get these random defects in different places, but on the average, you would get, 5 defects in your 12-inch wafer, okay? But for the sake of discussion, let's say we're talking about those defects are landing in the same place, okay? So in a second, you'll see where I'm going with this. So now let's say you have, on one hand, you had a very big design, very big chip. Okay, let's say it's a very big chip. I'm gonna really exaggerate the heck out of this. Let's say you could only get 4 in this wafer. Okay, and again, I'm gonna exaggerate. Let's say you could somehow magically make this chip, oops, much smaller. So what do I get here? So I get 4 parts here. This is a huge exaggeration, guys, but same goes through 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So this is, you get 56. Okay, so this is gross die per wafer. Again, this says how many geometrically you can fit into the wafer. Okay, so you get 4 here and you get 56 here. Okay, everybody's good with that. But the situation is really bleak here because how many good parts do you get per wafer? You get good parts per wafer, you get exactly 0 because your chip was so big, these defects knocked out every chip you had. Whereas here, look at the, so we got, these got knocked out, these got knocked out. Maybe let's click on this guy got knocked out, this guy knocked out, these 2 got knocked out. Okay, so I lost out of my 556 gross die per wafer. I ended up losing 1, 2, 3, 4, 5, 6, 7, 8, 9 parts. So what is that? That's 47. So in fact, this is even a much bigger effect than just the geometrical effect is what happens to, because of these random defects, you get, this is called the die yield, which is ratio of good die over the number of die per wafer. Okay, so this is called yield. And you hear this all the time, yield, yield, yield. If you listen to investor calls or you're in the semiconductor business, you're talking about the process yield, which says exactly this. How many good die you get. This gives you a real good indication of the manufacturing defects, but it also tells you how good your design was. Because you screwed up your design here, your yield is exactly 0. You paid for this wafer, you got nothing out of it. Okay, your yield here is 47 over 56. So it's 83% yield. Okay, so I exaggerated the heck out of this because, you know, this would like never happen, right? So maybe you'd end up with getting, so in our case, for example, I did it just because of, you know, I have a hard time drawing stuff and I wanted to show you guys the effect of these defects on having a large chip, how devastating it can be. But to various levels, this works for all sizes. The larger size, you know, this 20 millimeter compared to 15 millimeter on a side die, this $21, because, you know, this yield, I don't know, well, let's look at the yield. So this guy gives us, so back to, I'm going to come back to this website. Whoops. Oops, come on. Sorry, guys. Screen. Share screen. Back to our buddy here. Okay, so now you're seeing the web page here again. So this tells you, you know, we've got a certain defect density. Let's keep that the same. Okay, so this gives us 137 max die per wafer, but it said because the die is this 20 millimeters, 44 of these dies died. So that yield is going to be for, this is for the 45 nanometer process. That yield is going to be 44 over 137. So that's a 32% yield. And if I go back to my 15 nanometer design, that was smaller. That gave me 205 good dies out of 256. So that yield is 80%. Okay, so now if I, including the yield, if I look at the prices, you end up with, so $4,000. I get 205 good die. I end up with $19.50 for the 28 nanometer process. For the older process where the wafer price was cheaper, I actually end up with $68 per die. So a crazy, like the die was only a little bit bigger. You went from 20 millimeters on a side. So sorry, from 15 millimeter on a side to 20 millimeter on the side. But even when you went to a lower price wafer, there's a 3 times bigger cost for that slightly larger die, which seems only slightly larger, right? When you're designing stuff, 5 millimeter on the side doesn't seem that big of a difference, but it made a huge difference to your cost of goods sold, to your silicon price. And that's because geometrically, how many parts you can put in the wafer, and then how many good parts you can get per wafer. And it's really an exponential relationship. So, you know, when we talked about the effect of cost on engineering activity when it comes to NRE, an example was to go to a older process was, you know, you had to try to get your more performance out of a process to reduce your NRE to be able to go to an older process. Here, where it comes to is physically, and a lot of times what you're doing is you're not comparing necessarily across processes, but your manager is coming to you and it says, in the same process, in that 28 nanometer process, hey, 15 by 15 millimeters is too big. That's going to cost us too much. And so you're going to have to make it a 12 by 12 millimeter die as a designer, which means you have to shrink the size of your circuits. You have to optimize the physical size of your circuits to get the lower silicon cost. And we run into this all the time, right? It's always in every single design that you do. One, the question is what process it's going to be in. And the pushback from management, investors, everybody is put in an older process and give me the same performance because it's lower NRE. And the second pushback is, again, because of the cost, is make the size of the chip smaller, 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 because I get significantly lower cost per die. So again, in this quadrant of cost versus performance versus reliability versus power consumption, we end up with this physical size, performance versus cost, and how they affect each other. Okay, so any questions about that? I ended up talking a lot more than I expected to, but hopefully you guys got something out of it. Hopefully, like some of this stuff I think goes across a whole bunch of applications. So let's jump into, and if you guys don't have any questions, let's jump into the teams. Okay, so let's see any volunteers? Go first. Okay, sorry, I'm trying to figure out who is talking. Let me put you guys up.
Oh, Jarek.
Jarek, okay. Go ahead.
Let me just set up real quick. 1 second.
Gotta make sure I can give you the host. Where am I? Sharing.
Oh.
So you should be able to share your screen if you need to now.
We can go next if you want, if you are still waiting on Jarek.
Oh, did Jarek disappear?
No, I'm right here.
Oh, okay. Go ahead, Jarek. I mean, I was just giving you the host.
Couch. I'm just checking in with my partner real quick. Just checking in with Garcia.
I'm good.
You good? Okay. All right. So good afternoon. We're gonna be talking about me and my partner, Ms. Garcia. We're gonna talk about the A15 Bionic chip, commonly found in the latest iPhone 13. And then we're gonna be making suggestions on that. But let me show you the slides we have first. So just a quick comparison. We're looking at the A15 from the 2021 model, which is the iPhone 13. And we also got the A14 from the iPhone 12 2020 model. And if you look on the right side, you can see some specification on that. There's a couple of things that we kind of highlighted that we kind of want to emphasize on. So looking at the frequency, the process, and the transistor count, but also keep in mind the number of cores that we have on this one. So what kind of suggestion are we suggesting our company, Apple? Basically, we're suggesting that we prioritize more on the performance over anything else. It kind of goes in line with Apple's goal right now, where they kind of sacrifice a little bit of their profit in order to enhance their performance. And how do we increase the performance? So there's two ways on how we can go about this. The first way is increase the number of cores and or clock rate. And we'll go more into details with that one. And the second one is move from 5 nanometers to 3 nanometers. So the first one, we can always increase the processor core from 6 to 8. So right off, just to make a going back to the comparison, A14 had 6 cores, and the A15, the next year's model stuck with the 6 core as well. The reason for that is the more cores, theoretically, the more cores that you have, sometimes it consumes a whole lot of more power. So going from 14 to 15, it seems like what Apple did was they wanted to conserve a little bit of that power consumption, but instead they increased the clock rate on, going back to they increased the clock rate on the cores on that one. So, so we can either increase the core from 6 to 8, but the key to this is we got to balance it out, right? So as you can see, we have 2 core of Avalanche, which is the 3.2 gigahertz, and we got 4 the 1.82 gigahertz Blizzard. So what you want to do is you got to balance it out, right? So you got to have 4 of the high speed ones, which is the Avalanche, and then 4 of the Blizzard ones. So by doing that, we're kind of balancing the performance and the power consumption. On the other hand, you could actually just increase the clock rate at all. Stick with 6 instead of doing 8. So it sticks with 6, and instead of doing 3.2 gigahertz, probably bump it up to a more clock rate on that one. Better for much higher computing on your chip. And yeah, same thing they did with the 14 to 15. They stuck with the same 6 cores. They just upgraded the higher speed clock rate. And on top of that, the reason we actually want to increase the clock rate on that is because increasing the max frequency actually improves the performance. There was a study on one of the articles that we read that the more frequency per core you have actually resulted in 10.5% improvement on the performance. So other than that, we can go with that route where we go with the cores and the clock rate. But the second option that we do have is going from 5 nanometers to 3 nanometers. And my partner, Garcia, is going to kind of talk about that a little bit, and then we'll go from there.
So our plan is to move from a 5 nanometer to a 3 nanometer. And by doing so, it will increase the transistor count, which in turn will consume less power, and also it will produce less heat compared to the 5 nanometer chip. And by doing so, the 3 nanometer processor will be faster and it will be less affected by the heat. And so this is just some of the specs that we got. So on the chart on the right-hand side shows the comparison between the 5 nanometer and the 3 nanometer. And as you can see, the transistor count has increased and the transistor cost decreased. And when we switch from the 3 nanometer, the wafer cost will increase. However, even though we're increasing the price, it would only be around like 15% of the total cost to make an iPhone. So for the iPhone Pro Max, which is used, which the A15 uses, the cost is around $450 to produce, but the chip will only cost around like $15. So based on the research we found, the iPhone 13 has a 13% profit, and we get a good profit with our improved chip, and we get really good performance, even if the cost goes up a little bit.
Okay, sounds good. Okay, we'll test a bunch of these assumptions.
And yeah, these are just going to be the references that we had. Okay, but yeah, awesome. Any criticism or questions?
No, if you could send me the presentation, email it to me.
Okay, sounds good.
And we'll go through it. So today we're just going to try to hit as many people as we can, just to kind of see what path they're on. So thanks, guys. It looked good. I think it's a good candidate. Who'd like to go next? George?
Actually, would it be okay if we go next? We don't have as much thorough research as the other team though, but
okay.
I hope it's useful enough.
Yeah.
Are you cool with that, Ethan?
Yeah, I'm good with that.
Okay, let's
so
do
we
that.
got next one we got George and Ethan.
Ethan, yes.
Okay, guys, go ahead.
Oh, do you want to present, Ethan, or?
No, you have co-host, so you have to.
Okay.
Do I I can make Ethan co-host? Which one would you like? Or does it matter?
No, it doesn't matter. We're just going through the slides.
Okay, go ahead.
So for our company, aptly named Fake Chip Co., we are competing directly against the Arduino's Dewey chip. And we've selected this chip because it is more highly priced compared to other chips that are open source. And because it is open source, we are able to have a lot more data on it. So if George will go on to the next slide, we can see that the Arduino company itself gives us a lot of information just on the different technical aspects of it regarding the power, clock speed, memory of the device. And it even tells us the microcontroller being used, which the microcontroller itself is also well documented within our sources, but it's just like a huge paper document. So we would need to like cipher through it to determine what improvements could be made upon the microcontroller. Next slide. Here we have the full Arduino Dewey schematic. So we see a bunch of parts, including MOSFET, capacitors, multiplexers, and other microcontrollers. And from here, we can see in depth all of the measurements and everything needed to make the Dewey operate. So we could use this information in our own design to improve the performance while hopefully reducing the cost of our own product.
Okay.
The reason why we chose the Arduino Duo as an example is because of how much potential it has for like hobbyists to be able to use it. Mm-hmm. Besides the fact that I think a lot of the applications that we can use, we can definitely, we normally pay for the Arduino name, not for the chipset itself, right? They actually have over here we can introduce the schematics that they have. Well, at least the utility that it has and all the pins that you can use. But other than that, it is a pretty well documented chip, which yeah.
And just our various sources, including the microcontroller CPU datasheet.
Okay, looks good, guys. I think it's a good candidate.
Yeah, professor.
Awesome.
Thank you.
Thanks. Cool, guys. So who's going next?
Can we go next?
Russell?
Yes.
And okay. Oh, duh. Sorry, Russell. Like, should be making you co-host. Hey guys, when is this class over? 3:45?
Yes.
Yeah,
Okay, cool. Yeah. Okay, great. Everybody good? Anybody need a bio break, or we're good to keep going? Everybody's good? Okay. Go ahead. Sorry, Russell.
Okay, so the chip we researched was the Intel Celeron.
Sorry, Russell. Who's your partner?
Filbert.
Okay. Okay, go ahead.
So chip research was an Intel Celeron processor based on the KB Lake microarchitecture. So this is a WikiChip website that I found. So it has a lot of information, like the process is using, and it also has the block diagram.
Mm-hmm.
And a bunch of other things that I don't quite understand yet, I guess.
Okay, cool.
Yeah, and in case we need a specific one, we're looking at this specific, I guess, SKU. So I don't know if we need to have like a specific chip that we're trying to improve on, or can it be like a general, like Celeron?
I would, I think you'd call it something, call it a particular chip. So we have like single numbers to compare to. So what we'll end up doing is we'll come up with some assumptions, say for physically how big it is, what the wafer price was, what the costs are, what process it's in, what the clock rate would be. We'll make some assumptions about power consumption. A lot of it is we're like looking at the overall picture, but I think we need to, this, by the way, you do a lot at work. You just say, even if you're not sure about something, you state your assumptions, you give the reasons for assumptions, and people either say, oh, go check your assumptions in terms of how things are, or we say, okay, we'll accept those assumptions and then we're going to compare with that. So I think we want to make sure that like to be able to come up with a replacement or another part, we're going to have to like make those like specific assumptions.
All right.
So long story short, you're going to have to pick something, or if you're not sure, just call it some new SKU G3931, make up something. It's good enough but I think it's a good one. And are you guys thinking about, have you thought about what you're going to do to improve on it?
I mean, not a lot. Like,
okay.
I mean, I've heard like AMD's like chiplet design. So I wonder if that can be used. I'm not 100% sure.
Okay, that's cool. Okay, we'll sort of explore it as the semester goes. Awesome, that looks good. Thanks, Russell.
One more thing I was wondering. Yeah. I don't think Intel provides like a publicly available like data sheet.
Yeah.
So is that something we need?
Well, so this is another thing. So a lot of times you won't get data sheets, depends on or you won't get data sheets without signing non-disclosure agreements with people, blah, blah, blah. So we're gonna have to go do some digging around in conferences, some different places. And that's the kind of stuff we'll be working on, trying to see how we can do some detective work and see what this one might be like. Or we might have to do some assumptions. And again, we'll like state those assumptions and move on with it. So it's okay. I mean, I think there's enough here that we can work with. So it's okay. Because we're not gonna get, by the way, for you guys looking at these chips, we're going to be really looking at them at a high level. So don't worry about, oh, I don't understand how, this has this weird interface on it. I don't know how the heck that interface works. I need to go dig in to the schematics and figure out what the interface is. Like, we won't be getting to it at those levels. We'll be like making assumption about, and you'll see how the way we're learning. A lot of this class is about making sort of smart assumptions when you look at something. So you come up with power consumption assumptions based on clock rate and based on number of transistors, but the sort of block level stuff. So anyway, don't get too wrapped around trying to, dig into all the blocks, all this stuff. Just kind of generally understand the capability of this thing. But I get the sense there's enough here, and then with enough assumptions and maybe we do some detective work, we'll be able to have enough meat here to work with. So you're good.
Okay, thank you.
Yeah, sure. Sounds good. Who's next?
We can go.
Okay, Quinlan.
Yeah, so I'm partnered with Brianna.
Yeah, I'm here.
Make co-host who would like to.
I can share.
Okay, cool.
Professor, you can just enable the sharing from the security. Go to security and just uncheck the share your screen.
Security. Share screen. Okay, awesome. So cool. Thanks. Quinlan and Brianna. Okay, go ahead.
Okay, so we wanted to do the Intel i9-10900, and I think there should be enough information on this. Intel actually lists the specifications on their site, and they also have the datasheet available. So as far as I know, this should be enough. You can also find specifications on like other websites, but oh, that's not it. The Zoom thing is in my way. How do I move that? Does anyone know?
The Zoo thing? I'm not sure.
The Zoom like interface at the top. I can't change
tabs. You could like minimize it if you click like the drop down thing.
Okay.
You can also do control tab.
Sorry. Okay.
Control tab.
But yeah, Intel shows, as far as I know, enough information for this project right on their website.
Okay, cool. Yeah, I think you're gonna do Intel generally, for whatever reason, they do. It's a good candidate. Usually give you a lot of info. Okay, sounds good.
Okay, awesome.
Cool. So, okay. Who's next?
I can go, Professor.
Okay, Miguel. Okay. And who's your partner, Miguel?
Perla.
Right here.
Go ahead.
Let's see. Okay, let's hope it's sharing. Okay, so we're doing the AT Mega 328P. And oops. There's a whole data sheet for it. It's very descriptive. It comes with the features of it, comes with the pin configurations. It also comes with block diagrams. I haven't looked through all of it. I'm maybe gone through half of it, I'd say, but it's very detailed in what comes in the chip. and all the features that come with it. So improvements wise, I would say mostly I want to focus on performance base. In detail, I haven't gone through it yet, but I have a couple of ideas swimming around.
Okay, sounds good.
But yeah,
Does
this
it-
is very
have
detailed.
Have you run across any info about what type of process it might be being made in? Does it say anywhere here?
I don't believe I've gotten it yet.
Okay, scroll down a little, kind of slowly, just right there. Let me take a look. Can I tell anything from this? 2.7.
It's a microcontroller, Professor.
Yeah. Oh, yeah. It'd just be a microcontroller. Yeah.
Yeah, it's a microcontroller. This is actually the one that Arduino uses.
Yes, it's the one Arduino uses.
Okay, so we're gonna have to do some digging around, but I think you're gonna have a good chance with this one. Okay, sounds good.
Okay,
thanks,
thank
Miguel.
you.
Thank you, Professor.
Thanks. Who's next?
Professor, can we go next?
Sure. Who is that?
Daniel.
Daniel. Okay, Daniel. Thanks.
My partner is Jonathan Norris. Jonathan Norris, yes.
Great.
All right, let me share my screen. Here we are.
This is we've already talked about this.
Oh yeah.
Okay.
So, hello.
Hey.
All right. So yeah, me and my partner Jonathan decided to do the project on the TI TMS 320 C6455. So this chip is a digital signal processing chip that's made by Texas Instruments, and it was created in May 2005. Costs a little bit, but that's one of the goals that we do plan on working for, the chip, decreasing the cost, which we'll cover later. The main specs of the TMS 320 that we noticed was that it had 2 megabytes of RAM, 32 kilobytes of ROM, a clock rate between 720 megahertz and 1.2 gigahertz, and it seems that the clock rate is interchangeable, and a power consumption of around 2.3 watts, which is another goal that we want to decrease, which is the power consumption. With that being said, I'll leave it up to my partner, Jonathan, to cover the rest.
Yeah, can you go to the next slide? Thanks. Yep. Yeah, so this is just the general architecture of the chip, how it processes stuff. Can you just go to the next slide?
Mm-hmm.
Yeah, so what we want to improve are power consumption, price per chip, and if we can also hit on the amount of computation it does for fast Fourier transforms, as that's the main way that it's doing DSP. We can either do that through increasing the number of like CPU power for that so that it can compute faster, or we might be able to maybe change up the logic a little bit so that it is using a different algorithm that's a little more optimized and can maybe compute faster. And that might be a little more ambitious, but work more in line with reducing power consumption as well as maybe reducing price per chip.
Okay, sounds good.
If you go to the next slide, this is just the references that we have. We couldn't really find too much data on the size of transistors on the chip. That was the data sheet doesn't really mention it. It's more so about the software side of the chip and pinouts.
Got it.
Yeah.
Well, I'm pretty sure we can find something good. Knowing when it was introduced, and sort of the markets it's in already gives you some bracket of the type of technology it was in, and then we might be able to dig in a little bit more. So that sounds good.
All right. Thank you.
Good. Thanks, guys.
And then do you want us to just email you the slides?
Yeah, it'd be cool if you did that. By the way, guys, I was going to ask you. So what I would like to do, I think what it would make sense is us to have something like more like Google Docs or something where, we're just revving on the slides as opposed to passing them back and forth. Have you guys used anything in Cal Poly that's more like sort of in line with PowerPoint and all this kind of stuff? Or do you guys have a preference? What should we do? Any candidates? If like given would Google Docs bother anybody if we go that route? Because otherwise we're just kind of like, we're going to be revving these slides continuously. So just passing them back and forth is we're going to lose revs and stuff.
I think as far as options go, there might be something we can do through Canvas.
Oh yeah. Okay.
Yeah. Otherwise Google Docs works for me.
Canvas. So I'll look through to see what Canvas has, what options Canvas has, and then I'll let you guys know. Well, for now, just go ahead and please email it to me. But I think once I figure that out, I'd like to figure that out. Lorraine, do you want to make a point?
Yeah, we actually all have access to Microsoft OneDrive, so you can create like a class folder and everyone with their school emails is able to put stuff, and just like Google Docs, you can update it live, and you can also open it to like the desktop app, because I don't know if everyone else shares this preference, but Microsoft Word and Microsoft like PowerPoint and stuff is usually much better than like Google stuff.
Yeah. I think that's a winner. That sounds good to me. Anybody have anything against that? If not, going once, going twice, I think sold. So I will see if I can create a OneDrive, and I think that's the good way to go. Thanks.
Are we still doing presentation?
I'm sorry. Yeah. Sorry for the distraction. Go ahead. Who's next?
Okay.
Kushal?
Well, yeah, we'll go. Alex, do you want to pull it up?
Alex. So it's Alex and Kushal. Is that who's
okay, Alex, I see you. Yeah. Mm-hmm. Yeah. Very funny, Alex. So this is our chip. It's called the MCP7940, and it's a real-time clock / calendar. Next slide. So this is just like a background of all the people who work for Microchip. On the announcements, it said on the presentation, you should have like the founders, like the leadership and the finance. So basically that's what we research more than the actual chip itself. Yeah.
Interesting. Okay.
Yeah. So this is literally just the financial status of the chip.
Of the company, I guess. Okay, financial status of the chip.
Well, I don't know.
No, I think this is more the company, isn't it?
Yeah, this is more of the company, because that's what it said. But
what are you referring to, Alex? Where were you saying it said? What said?
So Alex's mic doesn't work. This man needs a new mic. But I think he's just trying to say that the 10K shows the overall like financial status of the company.
Yeah, but why are you guys looking at the financial status of the company? Just out of curiosity. I mean, it's interesting, but
in the announcements it said look at the financial something, and I just took that as finance. I'm pretty sure that's what it said in the announcements.
For that I put up?
Yeah.
Oh, well, maybe I stirred you guys wrong. Can you pull it up?
Sure. Pull it up, Alex. I might have read it wrong too, but no, I think it was the presentation. Right there. The proposal consists of a presentation to the fictional company management, investors, etc. Compare your solution to the existing one.
Yeah. But I mean, you don't like when you like make a presentation to the company management. So are you guys making a making a presentation to the microchip company management?
Yeah, pretty much.
Yeah,
that's what I thought. So like, this is our competitor. This is how much they're losing. But if we make this chip, it'll be even better.
I see what you're saying.
Yes, I didn't know what kind of presentation you wanted, but
got it.
So next week it'll be better.
I mean, okay, but it's not. I mean, I like where your head's at. But yeah, but like what you want to do is we want to focus on the chip. But it makes sense what you guys did now. Go ahead.
So the modifications that so since I'm more of an embedded firmware engineer, I mostly focus on like the communication aspects of it. So I noticed that the chip is using I2C, and the highest baud rate it has is a 400 kilohertz. And so what I was thinking was changing the chip's communication protocol from I2C to SPI. Might not make sense, but that's basically one of the performance. What is the word I'm looking for? Performance modifications that we were thinking of. The next one would be just Alex. All right. So the next one is, if you look at the block diagram here, you can see that it uses a square wave for its output. And instead of using a square wave, if we did a PWM, I feel like we would have more malleability, I guess, and more free control of how much power we're consuming, or how much it's outputting.
Okay, so
that's
now, okay, gotcha. So now so this guy, I mean, it's not that I don't like the chip. In fact, I like it because it's kind of a small chip. You guys can get your arms around it. How would you decide like what the physical size of this chip is to figure out, like how would you come up with like cost of this chip? It's something you need to think about, or we need to think about. But it's definitely like an interesting chip, but we'll have challenges. So let's say you're good for now, and then we'll see where it takes us. I like the fact that it's a small chip.
There's a lot of documentation on it just because it is for microchip. So I don't think we'll have any problems finding any more like specifications for it. And the next presentation will be a lot better, just because I didn't really know what we were supposed to do in terms of modifying this chip, because I'm very new to integrated like ICs. So
yeah. No, it's I think the main thing I want to make sure, as far as you guys presenting right now, is get a feel like, is this a good candidate for us to be able to get information on? Gotcha. So I think it's probably pretty good. So let's go with it. Okay. Cool. Thanks, guys. Who's next?
No problem.
We can go next.
Go ahead.
All right. Okay, we'll go next. So my partner is Eric McDonald.
Yep. So Eric, and who is it? Yakov and Eric, or who's sorry? Okay, right. Okay, guys, go ahead.
Okay, so we chose the AMD Raven Ridge APU, which was the first APU they did with the Zen architecture, released in 2017. And we primarily chose this chip because we found this pretty useful presentation online they did in Hot Chips back in around the same time. And it has, a lot of information about, comparing it to previous generations of APUs they have done, and some stuff about the architecture and, for instance, transistor count, die size, and, the fact that it's 14 nanometer process. And there's a lot of stuff I don't understand, but a lot of graphs as well.
Mm-hmm.
CPU speed, time versus frequency, and also some thermal information.
Mm-hmm.
And also, obviously, there's a lot of information online, like Wikipedia and stuff like that, about, you know, clock speeds and power, price, you know.
Got it. Looks good. Good choice.
Okay.
Plus, it has a super cool name, Ryzen. Yeah. All right. Thanks.
Thank you.
Thanks, Jacob.
Could we go next, Professor?
Yeah.
Okay.
This is Gabriel?
Yes, Gabriel and Talon. All right, I think I can't share because someone else is sharing.
Can't bump them?
It says you cannot start screen share while other participants are sharing.
Huh.
There
So
we go.
Jacob, do you have to? Okay. All right.
Sorry about that. I was still sharing.
Oh, it's all good. Okay. Can you see?
Yeah, go ahead.
Oh, great. So the chip that we chose is Sony's ECE4203 It's a CCD image sensor for video cameras. So Talon's going to do the next 3 slides.
Yeah, okay, go to the next slide. So yeah, the CCD is essentially the charge couple device, and it contains an array of coupled capacitors that like transfer electrical charge between each other. And to the right is just like a screenshot of our chip, the way it looks, and a quick summary of what it's capable of. And since it involves a lot of imagery, it involves like sensitivity to light, low smear, or yeah, just stuff like how to improve an image looks better. And could you go to the next slide? And yeah, the way the CCD sensor works is that it absorbs photons in that first picture, as you can see, and then it converts them into electrical charge, store them in arrays, and then output an image based on how light and dark each pixel is. And then the chip runs through an algorithm through each pixel to determine the appropriate coloring using the Bayes filter, as you can see on the very last picture. And next slide. And then with this chip, since it involves images, the common problem we go through is the blooming effect, which is essentially the bleeding of lights in images. And we can't have that. If we were trying to improve that, we would have to include like an anti-blooming component. And from there, we can reduce the flaring of an image essentially. But the big trade-off to including the anti-blooming component is that with less charge going through the device, our image isn't as clear to the eye, and the image may be blurry and then generally unclear. So we hope to fix the problem by increasing the chip sensitivity to light, which my partner will talk about in the next slide.
Okay, great. So after going through our data sheet, we're actually able to find a lot of very interesting and helpful information regarding our chip. So that's great. There was a lot of websites that we were able to come across. So one of them was the concept of sensitivity. So it intensifies CCD with fiber optic coupling. So this is one of the solutions that we were able to find. So an image intensifier would help increase sensitivity of a camera by amplifying the input light signal before relaying it to the CCD/CMOS sensor of a camera. So this is just one of the enhancements that we could do to the chip. So the image intensification can be accomplished by means of a relay lens. A lens coupling is flexible, but the downside is that a lens coupling has a low transmission efficiency. So there's like a trade-off there caused by the limited aperture of a lens. So in like application, this would help like say like security cameras have a better pixel density when being used for like regarding video feed. Next, we also saw that this chip lacked like any sort of cooling mechanism. So we researched like cooling for CCD chips, and we were able to come up with like that thermal noise like really affects these sort of chips, and it increases what's known as dark current, and that could distort the image. So we found that if we were able to reduce the temperature by at least 20 degrees Celsius, we could reduce the noise by 10 dB and thereby improve dynamic range by 10 dB. And in outdoor environments, temperatures can exceed like 40 degrees Celsius. So if we were able to come up with some sort of cooling mechanism, we'd be able to prevent the image quality from deteriorating. And thermoelectric coolers designed to operate at high temperatures can be used to reduce the sensor's temperature below its maximum operating temperature and maintain a high image resolution. So this is just another enhancement that we're looking at. And last, we just have a big bibliography of our resources. There's so much more and so many things that we're ready to delve into. Me and Talon have not had an experience with these sort of chips before, but we're very excited to get started and learn more. And that's it.
Okay, thanks. So, you know, this is what I do for a living. So I'm very familiar with this. It's near and dear to my heart. But so I'm going to ask you why you guys pick this thing, like how much you guys want to work on it, because that's important. But the way I look at CCDs, it's kind of more like an analog chip rather than a digital chip that, you know, we're talking about. For example, everything you mentioned is all good stuff, by the way, but none of it is like really like silicon design. You're talking about, you know, putting fiber optic plate on it, or putting thermoelectric cooler on it, or improving the anti-blooming or say sensitivity, stuff like that. But we're looking for a project where you're like doing something to the silicon itself, maybe changing the size of the chip, running it faster, those kind of thing. And this is kind of like, especially CCDs or analog things. So normally I would say like this may not be a great candidate, but like, is it something you guys are using at like an internship at work? Are you like excited about image sensors generally?
Yeah, sorry. I think now that you say that, everything that we were kind of researching were sort of enhancements, I guess, on the outside of the chip. So
yeah.
So it seems like, and I'm just realizing that right now. I think because when we were looking at the data sheet, we were sort of seeing all these like new like terms we had never come across before. So maybe we'll focus more on like actually modifying the chip itself, and rather than like, I guess, peripheral enhancements to the chip, if that's the correct way of saying that. But yeah, so we'll definitely steer in that direction then.
So let me give you, like, if you want to stay in the imaging space, which is, you know, I love that. I love this stuff. You know, let me give you a suggestion. Check out a company called Umbrella. I don't know if you've heard of them. Ambarella, Umbrella, and maybe it's one L or two L's.
Got it.
And so they're traditionally their customer has been GoPro cameras. But now they're more moving towards more like automotive and stuff. But what they work on is the digital processor chips that takes data from these kind of sensor chips and does all the processing on it. So that's maybe like a better candidate because it's like a fully digital chip.
Okay.
It's doing stuff that we can get around it. So check out Umbrella. They're sort of pivoting, you know, going from GoPro to automotive. So I'm gonna guess they're gonna be releasing, you know, they're like having a lot of announcements and stuff like that. So there might be a lot of good stuff about their chip. So my advice is maybe if you want to stay in imaging, but more in line with digital, check them out.
All right, will do. Thank you so much, Professor.
Okay, thanks. Okay, next.
Can I go next?
Okay, go ahead. So it's Victoria.
Yeah. My partner is Jonathan Nguyen.
Hi, I'm here.
So unfortunately, we do have the same chip as another team, which is the 18 Mega 328P. It is a very popular chip because it's used in like all the Arduinos. But like I said, it's like there's really good information. There's a datasheet block diagram. There's a packaging of the chip as well inside of here down below. Which I know you talked a little bit about, like the silicon making of the chip. So I think that would be really useful. And then I think in the sense of like ways to improve it. Well, when the actual microchip website has all these features about like CPU speed, just power consumption, like performance information. It has a development environment, as well as I think what's important is like how at least Microchip is trying to sell it. So the packaging media and price per volume. And And then I guess ways we are thinking about improving it is to optimize power consumption over processing speed, or adding like a USB module so it can compile with USB 2.0, or yeah, yeah.
Okay.
But that's kind of the research that we did. And then Arduino does have their own set of information of how they used it, but if we're talking specifically about the chip, I think that goes more in a low scale manner. So
yeah. So, I think, for the time being, we don't seem to have a lot of duplicates. So let's just say it's okay for now. If you end up with a bunch of duplicates, I might come back and ask you guys to try to pick something else. But so I like this because there's probably good info, obviously, like open stuff. But like the thing you guys and also the other guys working on Arduino and stuff you should be worried about is like this gives you like the size of the package, but what's the size of the chip? Can you find that? We're gonna have to do some detective work on that. But I think it's a decent candidate. So let's say it's good for now. So sounds good. Okay. Thanks, Victoria.
I guess we'll go next.
Kyle. Was it a A10 you're standing next to?
It's a P51.
P51. God, I can't see it. I'm going blind. Okay, nice. Thanks. Who's your partner, Kyle?
It's Rachel.
Rachel.
His partner.
Okay. Go ahead, guys.
So unfortunately, we also have the Atmega 328.
Okay, we're gonna
So
have
is
to
that going
pick
to be a
something.
problem?
I think it's starting to be a problem.
Okay.
You guys, you're pesky kids. What made you? I guess this is a question for you, for Victoria. I guess I'm trying to think. Was it George who picked the? Who was the other team?
No, Professor, it was me and Prella.
Okay. What made you guys pick this one? Why is it so popular? Is it something you've used in a class? Or?
Perla's currently using the Arduino Uno for her senior project, so we kind of just got it from there.
It was just easy to pick it because of that. Yeah.
I chose it because it's on the Arduino, yeah, and I'm familiar with that.
Okay. Okay, yeah, like sort of 3 duplicates ends up being a it's kind of like starts being a little too much, because that also like it'll be hard for you guys to pick something that'll be like significantly different than the other team to optimize. So my suggestion is you guys get together, like the 6 of you. I mean, maybe there'll be more joining your group, and try to sort of like figure out like if you can pick something else.
Okay.
Or pick something similar. Okay.
Okay, sounds good.
Okay, that's fine.
Okay, thanks. But I hate to do this because it's pretty cool that you guys are using it. So I really like that because it kind of gives you guys something to sink your teeth into. But yeah, like 3 teams starting to get a little too much. Sorry, guys. Go ahead. Who's next? Is it Rachel? No, Rachel was on the previous team. Who's next?
I can go next if that's okay.
Okay, Kathy, go ahead.
My partner is Paul, but he couldn't make it today. So
okay.
It's just gonna be me. So we were thinking of choosing the Google Tensor because it seems like somewhat of a simple chip to improve on, because when you read a blog post about it, the main point of the chip was just to use machine learning to improve like photos and like videos and stuff like that. And when we looked at the specs of the Tensor, it looked like it looked like the clock speed could be improved. So it dedicates 4 cores for like low powered stuff so that it saves like a lot of battery life. And then there's like 2 cores for mid range stuff, and then 2 cores for like high end like performance. So we were thinking we could improve on the high end performance and maybe even improve on the power efficiency for the low core stuff, because I think a lot of people don't want their phone battery to be wasted when like it doesn't need to be. So that's what we were thinking of doing for the Google Tensor. But we can't really find a price on it. Like the only price on it is with the phones that it comes with, which are the the Pixel 6 and the Pixel 6 Pro. But yeah, that was our plan for the Tensor.
Okay, that's a good. I think it's a good one. I think we'll be able to find a lot of stuff on it.
Okay,
cool. Sounds good.
Thank you.
Who's next?
Professor, can we go next?
Yeah, sure. Go ahead.
All right, Fong, if you could share your screen.
Jonathan.
Go to the first slide. All right, so my name is Jonathan Arbolado, and then my partner is Fong Lee, and then we're going to do the Qualcomm Snapdragon 855 chip. You'll usually find it in your Samsung Galaxy S10, S10 Plus, S10e. And then go to the next slide. Fong will talk about the features.
And here's the feature and specification of the chips that we found so far. It was first introduced in December 5th, 2018. And this is feature and specification.
Cool.
Yeah, and this is what we find so far for the improvement performance from the previous chips. And the downside of this improvement is heat. It will start gathering heat after about 30 minutes plus of playtime. Yeah, and I will pass this to my partner.
Okay,
and then
I think you're gonna, yeah, go ahead.
Oh, sorry. So the next couple links are just a couple benchmarks. So like for that link, it was just benchmarking of performance of gaming, just usual stuff that everyone likes to rave about. And then the next link, if you could go back to the slides, Paul. We also use WikiChip to bring out some more details about the 855. And then the last link is what we're going to use for improvements. So since it's a previous chip and we already have the 865 and the 888, we were going to look at what they improved and see how we can use those techniques to improve the 855.
Cool. That's a good candidate, guys. Nice.
Yeah, thank you.
Okay.
Hi, could I present? Yeah.
Sure. Go ahead, Jaren.
All right. Can you see my screen?
Yeah. Jaren, who's your partner?
Oh, Lorraine.
Hello.
Hi. Go ahead.
All right, so me and Lorraine picked the Semtech GS12090, which is a SDI chip, and it runs at 12 gigabits per second. And basically what the function of the chip is to do is drive a cable that sends a 4K signal, and it could also equalize a signal, so receive a 4K signal. And it could also adjust to different resolutions like regular HD or like 720p. This is the data sheet that we have on it. It's like the main source of information that we could find on it. It has the list of all the key features and how to use the chip. And there's also the functional block diagram, which shows like the basic blocks of the chip. There's also the rest of the manual is pretty much like the registers and how to control the chip and everything. And for improvements, I was thinking of changing like how to control it and everything, because using registers and everything to control like the modes of the chip and getting data from those registers is kind of like confusing, because I'm kind of working with this chip right now as well. And yeah, that's pretty much all the information that we have on it currently.
Okay. So Jen, you said, I was going to ask you why you picked it. So you said you're working with it?
Yeah, I'm working with a board that has an FPGA, but it also has this chip to receive and send out video signals.
Yeah. I think it's pretty, like, I love this stuff. And so from that point of view, it's really cool. One slightly dangerous thing, but I think we can make some estimates, is I don't know how much like information you can get about it besides the data sheet. But I think we can make assumptions, and it's like, you know, SDI chips and high-speed clock drivers are near and dear to my heart. So I think it's good. Let's do it. And plus you're using it. So sounds good?
All right, thank you.
Okay, thanks. Who's next?
Professor, can I go?
Sure, go ahead, Brian.
All right. So me and my partner, Julio Ortiz, we were thinking about doing the Qualcomm Snapdragon 212 mobile processor. So basically, the Qualcomm Snapdragon 212 is an entry-level SoC for Android-based tablets and smartphones. It contains a 4-arm Cortex A7 CPU core with a clock rate of up to 1.3 gigahertz and an Adreno 304 graphics card, LPDDR2 and LPDDR3 memory, and a lot more terms that I personally am not really familiar with at the moment, but hopefully I will be as soon as we get the class going. So this is the block diagram that my partner found. If Julio, you want to expand on it.
Yeah, so the block diagram is mainly the pinout for the entire, or at least for the CPU of the Snapdragon 212, because it has different components like the CPU, GPU, a DSP, and things like that. And then if you want to go to the next slide, actually, we also have the power schematic for the chip itself. And I think we found a good amount of resources, like a full data sheet for it. And then there's also, Brian, actually, if you want to let me share the screen, I can show some of the links I found with information on it as well.
Yeah.
All right. So, this one. Yeah, well, this is one of them.
Okay.
But let me see here. It has things like general info, things that it supports, the semiconductor size, clock speed, and a lot of other things as well regarding performance. And even we use the IEEE, the database that you suggested, and there were also quite a bit of articles there referencing the CPU specifically. So we're thinking about improving the CPU. We just haven't decided exactly what we're going to focus on to improve it yet.
Okay, looks good. Good candidate. Thanks, guys. Who's next?
I could go next.
Okay.
So let me share my screen. My partner is Alston Borg. Here. We're not very confident about the chip. Maybe you wouldn't approve, but I find it very interesting. So I wanted to improve on BM1398, which is an hash chip. It's used in ASIC machines, which is trying to convert any sort of energy into encrypted information, which eventually rewards you with money. And here there's an exponential improvement over the years because the hash rate, I don't know if you can see this, it's growing exponentially. Here I don't have a lot of information on the chip. I was able to find some research on it, but not specifically on the chip a lot. Yes, that's basically it. I have a data sheet for it, but not for the latest one. It's for BM1385. So that's basically it so far.
And the name of the company who puts it out is Ant
Miner.
Miner.
It's actually Bitmain.
It's what, sorry? Bitmain?
Yeah.
Okay, sounds good. I approve. It's exciting.
It's this.
The coolest thing in the world to go is to go directly from electrons, turning electrons directly into money without going through intermediate stuff. So I really.
Yes, right now if you have any.
I like that concept.
Yeah, if you have any sort of excessive energy, like if you're producing natural gas, and if you have excess energy, you could literally turn it into money on the spot. Otherwise, you would have to spend a lot of money on transportation or other stuff. Yeah.
Nice. Perfect. Good chip. Sold.
Okay, great.
All right. Who's next?
Hello, Professor. Can I go?
Yeah, go right ahead. Is it Sean? Cool. Okay. Go ahead, Sean. You might be muted. I can't hear you.
Oh, there you go. Okay, got it. So we chose the Z-Wave Gecko Wireless SoC. It's by Silicon Labs, and it's a radio frequency, like modem type of chip. And this is the information we found on it. Key features being the processor is ARM Cortex M33, and it has 512 flash and a 64 KB RAM, and a few other features.
Okay.
And this is a brief description. So it's mostly used in like security, home security, lights, bulbs, and automation type of stuff. And this is the basic block diagram for it. Right here.
Okay. Cool.
And we also
Yeah.
found a lot of the data sheets.
Okay.
Yeah.
Nice. Okay, I'm familiar with this stuff.
Right.
Okay, sounds good. So we're going, guys. I'm getting notes that we're going a little bit over, but whoever's like presented wants to pop out can go ahead, or even if you haven't and you have to run, it's okay. By my count, we have maybe 3 or 4 more teams. So if you haven't presented yet, and if you can stay, so please go ahead and we can sort of get it all done today.
Professor, can you present, please?
Sure, go ahead.
It's going to be me and Shah Zaman. Do you want to share your screen? I hear my echo, by the way.
So we sort of chose this chip prior to knowing what the objective was. That we were trying to outperform or reducing costs. So we're not going to go with this at all. But gathered information on it. nonetheless.
So you guys are more scared of Jarek and Isabel because they're picking a 15 bionic chip to improve on.
We kind of did get that feeling after we saw the presentation. But the idea was like choosing something related to Apple. It's going to be more popular. And as we were going, like we thought that we're going to have more resources and it's going to be easy to do a research on. But by the time that we try to like find like data sheets and getting more into deep, it was much complicated and harder to find resources.
There's no data sheets whatsoever, so.
Okay. Any thoughts on where you're gonna look next?
Probably just research on IEEE, explore, try to find something.
You know, guys, I didn't see any NVIDIA chips so far. So if I was just gonna, and they sometimes publish stuff. So if you guys need a pointing direction, so you could try to look at NVIDIA.
Okay. We can look at that.
Yeah. Okay. Thanks, guys.
Thank you.
Thank you.
Professor, I need to go to work. Can we present next week? Would that be okay?
Sure. Ronaldo. Who's your partner, Ronaldo?
Tree Nguyen.
Okay. I hate to tell you this, but I'm an Iron Maiden fan myself, so I can't say no.
Right on. Thank you.
Okay, sure. Anybody else? Who's next? Everybody else? So Tree, you were there, Russell. Alan, were you already a part of the team?
Yeah, we can present.
Okay.
So I'm Andy Chang, and I'm partner with Alan.
Okay. Okay.
So just as a quick run through, originally we were planning on using this Intel Core i3 Gen 6, but as we were looking through like the stuff, we have some specs on it, and we had an idea on how to improve it. But when you actually look through kind of the stuff, there's not actually all too much information on this chips in particular.
Okay.
So we were thinking instead, so like we have general specs, and we have some like others that are some other chips that can be used, kind of like we're not going to use that one. And then we found like a data sheet for like for this specific one, but we're thinking about moving instead to the i7.
Okay.
To use that, so we have some specs for this one too.
Okay, so you have more specs. You think you can get more stuff for the i7?
I think so, because when I looked through is this the right screen? When I looked through like the Google Scholar stuff, because I used Google Scholar to see if there was any like research done on it. There were a lot more papers published on like the i5, i7, i9, rather than the i3 itself.
Okay.
I don't know why, but I think probably the i3 is too old, I guess. So that's why we wanted to move to this one.
Okay.
But so far we don't have too much info on the i7 or i9, or we might not even, it'll be between the i7 or i5 or i9, but we want to go with one of those. Is that okay?
Sure, that sounds good.
Okay, then I guess that's it for our presentation.
Okay, so i7.
And then we'll have a better presentation next week.
Okay, sounds good. Okay, cool. So anybody else we missed so far? We've got everybody. I think we should be close to everybody. We've already got everybody. So I think we just have like a few teams that we're all sort of picking the same Arduino thing that need to rethink. And then the guys doing the CCD, I think we need to rethink, but I think everybody else is on a pretty good path. So sounds good. I'll if you guys could all email me your presentations, and we can go from there. Thanks, guys. Oh, Louis, did you have a question?
Yeah, I was just wondering, what do you recommend? What chip would you like go over or highly recommend?
Yeah.
Or sort of speak like more, it's going to be more interesting to work on.
Yeah. You know, I don't know about chips, but I would recommend, that's kind of why I recommended NVIDIA for you guys, because I'm really think it's an awesome company and they make really interesting chips. And they have chips all the way from stuff that does, you know, for server farms that is super high performance stuff. They have stuff for cars. They have stuff for, you know, they have this sort of handheld processor, the Jetson board family that I think is pretty cool. So, and they publish, so I've seen sort of interesting data from they're like a sort of a real high performance company I respect. So I think just look at NVIDIA, and I think it's more important that you like, okay, so I'm gonna just go on a limb and say NVIDIA, pick that. I think it's gonna be good. And then just pick a few things and just, I think unless you have like a real love for something, like some specific thing, or you're working on something, like the guys working on SDI cable driver are working on it, so I think it'll give them some hook. I would pick something where you immediately see, look, there's a lot of data, they've got publications, there's stuff about which process it's in, there's stuff about die size, that kind of thing. Then it'll make it easier for you to like proceed with the presentation. And again, I think NVIDIA, once you knowing what little I know about you, Louis, I think you'll be really intrigued by the company, because they're really like doing well, and they're like a real, I don't know if you've heard of them or know anything about them, but they're really doing a lot of good stuff.
Okay, thank you, Professor.
Sure. Okay, guys. Have a good weekend.
You too,
Sorry
Professor.
to keep you guys.
Wait, Professor, I had a quick question.
Yeah,
would it
what's
be
up, Brandon?
too late to change our chip by next Friday if we were to do maybe just research on another chip we might want to try to do?
No, I don't think it'll be too late. What I'm trying to look you guys up. What did you? Sorry about the dog noise in the background there. Brandon, why can't I find you? What was the chip you guys had?
It was the Z-Wave Gecko Wireless.
Oh yeah. No. Was there something you were thinking of?
We chose a chip based on radio frequency, but I was thinking something more DSP related, maybe something that's commonly used within the medical field or within machines that use it specifically. I was just trying to see if maybe there was something like that, if I could find something, but if not, then this is a good candidate as well.
Yeah. No, I think it's still early in the semester. We're not gonna be like, we're not jamming through this that fast. We're gonna be like cycling between the presentation work and projects and stuff. So you're okay to change it. And then, you know, there's like 4 or 5 teams that are probably gonna need to pick something else. So I think it'll be fine.
Would you have any recommendations for the criteria that I mentioned?
Well, so you said medical. Did you mean medical instruments?
Yes.
That's a tough one, because I don't really know. You know, like if you're talking about medical companies, there is God, what's the name of them? I can't believe I'm having a mind fart here. There are companies that make like chips for like pacemakers and things like that. There's good information about. I don't know if there's a typical chip that medical companies would use. Just like the market's not big enough that they would like have like standards or something that I'm aware of.
I see. Okay.
So, like check out, this is, again, may not be what you have in mind, but check out Medtronic, MEDTRONIC. And again, these guys make chips that are for like going to stuff that you embed into your heart or like in your body. They're kind of like the gorillas in that part of the business. Like if you have a medical chip, but it's not into really, normally it's not like doesn't go into medical like instruments. It goes into, it's actually something that like tests your blood sugar level or so on and so forth. So, but I'm not sure that's what you particularly have in mind.
Okay, I see.
But yeah, besides that, I'm not sure if I don't think there's any companies that, am I missing something about companies that would do, why are you particularly interested in medical instruments?
It's just, that's just kind of what I was interested in for a relatively long time, going into DSP, learning about DSP and et cetera. And I just wanted to see if I can do some, apply my knowledge of VSLI within that field. I just, yeah.
Well, poke around this weekend. If you could send me an email to remind me, and I'll see. The problem with them, that's not a problem. I mean, this is a great, I think, by the way, I think the health life, they call it generically life sciences. I think it's a great field for new products to get into, cool stuff, lots of opportunities. So I think it's a great field generally to sink your teeth into. But what makes it really good for American companies, new businesses, whatever, also may make it difficult for our presentation. So what makes it really good is it's, there's like a lot of small companies, not like high volume. A lot of stuff is expensive. Yeah, I mean, that's good, right? You can kind of sell stuff that you're making for higher prices, lower volumes. There's a lot of customization, but it also means there's like not, you won't find like a Qualcomm necessarily in medical, or like an Intel in medical. I mean, people I'm sure in medical use Qualcomm and Intel chips, but there's like those kind of things are that I'm aware of. But I'll look around for you this weekend.
Okay,
if
thank you.
Just please remind me, because I have like a real memory problem. So just shoot me an email and remind me.
But the Medtronic suggestion actually greatly interests me, especially with being able to insert chips into people and into that aspect. So I think that actually, I know where to kind of start now.
Okay, yeah, and they're like the gorillas. They're in that field. I think it's lots of cool stuff they're doing.
Okay, thank you, Professor. Have a good one.
Okay, you too. Take care. All right, guys. Bye.